Check 1 2 3. 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 Right, good evening everybody. Sound check. Can you hear me loud and clear? Is it loud and clear? You can put in the chat. Right, good evening everybody. Sound check. Can you hear me loud and clear? Is it loud and clear? You can put in the chat. Okay, great. Right. Welcome again everybody. Week number 5, day 2. So we are discussing the 2004 A-level question paper. Yesterday we did 20 MCQs, 1 structured, 1 essay. Right. So moving on, today's work, day 2 work. A coil metal wire made of a material of linear expansivity 2 × 10⁻⁵ has n number of turns. The temperature of the coil increases by 1 degree Celsius while keeping its radius R constant. The number of turns become n plus 1. So you can take the initial length. Initial length is 2 pi r times n. So one coil is going to be 2 pi r times n. Final length is 2 pi r times n plus 1. So here we can say the expansion delta L is L2 minus L1. L2 minus L1. That's 2 pi r n plus 1 minus 2 pi r n. That is your delta L. Simplify this. Delta L is equal to 2 pi r n plus 1 minus n. So delta L is equal to 2 pi r. Delta L is equal to 2 pi r. Okay. So here we can say delta L is equal to L1 alpha delta theta 2 pi r n. Alpha is equal to 2 10 to the power minus 5. Change in temperature is 1 degree Celsius. 2 pi r cancel off. Simplify this carefully. 0.5 10 to the power positive 5 is n. So 5 10 to the power 4 is equal to n. 5 10 to the power 4 is equal to n. So our correct answer is answer number 3. Correct answer is answer number 3. So initial length is 2 pi r. If you look at this here, this radius is r, 2 pi r times n. Final length is 2 pi r times n plus 1. Difference in that will be the expansion. Once you need it, carefully write it down. Right. Moving on. When 1 gram of each of the gases of helium and neon are separately enclosed, and argon are separately enclosed in the same container. Keyword here, same container. So same container will come in Dalton's law of partial pressure at the same temperature. The ratio of the pressure exerted by the gas respectively are. So if you take here PV is equal to nRT. Same container means what are the characteristics? Same volume, same R, same P. P proportional to N. Mass over molar mass. M is also same. Pressure is inversely proportional to molar mass. So the pressure of helium to pressure of neon to pressure of argon, that is 1 over molar mass of helium, 1 over molar mass of neon, 1 over molar mass of argon. So here helium is 4, neon is 20, argon is 40. 1 over 4, 1 over 20, 1 over 40. Correct answer is answer number 1. Right there. Since it is the same container with the same mass, we can say that the pressure is inversely proportional to the molar mass. Okay, no? Right. A thin metal plate PQ is inserted between the plates of a parallel plate capacitor, so that it's parallel to the capacitor plates as shown in the figure. If the area of the plate is same as the capacitor, the new capacitance R. Look at the board carefully. So earlier the capacitance here was C, the distance here is D. Now the distance here is exactly half D over 2. Area of the plates is A. Okay. So earlier capacitance, initial capacitance A epsilon naught D. Now how many capacitors are there? 2 capacitors in series. This is similar to 2 capacitors connected in series. Capacitors in series are like parallel resistors. Multiply both the capacitors, divide by the addition. Multiply both the capacitors, divide by the addition. Sorry. Multiply both the capacitors, divide by the addition. You will get C1 divided by 2. C1 is A epsilon naught, area is same, distance is D over 2 times half. 2 and 2 cancel off, A epsilon naught D. What can you say? Epsilon naught D is equal to C. So equivalent capacitance also is equal to C. Equivalent capacitance is also equal to C. Equivalent capacitance is also equal to C. So here final capacitance. Final capacitance. So capacitors in series are like resistors in parallel. Capacitors in series are like resistors in parallel. So you can multiply both the capacitors, divide by the addition. These are basic things which you all know. Yeah? These are basic things which you all know. From there you can get the equivalent capacitance. Substitute there for C1. From there you can get the required basic relationship. Yeah? Basic relationship. Right. Question number 4. An object of mass m, velocity u, moving on a smooth surface in the positive x direction makes a perfectly elastic collision with the identical object B which is at rest. Identical object means object having the same mass. No need to draw it because they are given you the object. There, they are given you the object. After collision, the velocities are. Now this you have done many times. You have done this. Equal masses means maximum transfer of kinetic energy. Equal masses means maximum transfer of kinetic energy. That means A will stop. A will stop. B will start traveling with the velocity u. So correct answer is answer number 1. Correct answer is answer number 1. These are very direct from your theory directly. There. These are there in your theory. Please check your theory note. These are directly there from your theory. Okay, directly there from your theory. Next one. In the potentiometer circuit shown, the indicated balance length L obtained from the cell P having an internal resistance, here there is internal resistance, okay, is simple L, right? Now at the balance point, what do you know? So at the balance point, what do you know? These are the conditions. At the balance point, what do you know? No current through the galvanometer. No current through galvanometer. No current through the galvanometer. If there is no current passing through here, is the internal resistance important? No. Why? Potential difference across the internal resistor will be 0. Right. So what can you say about the current here? All the current will pass through that point. All the current will pass through that. This is your primary circuit. We call this the primary circuit. And this is your secondary circuit. This is your secondary circuit. Okay, no? Primary circuit is on top, secondary circuit is at the bottom. Right, carefully look. Now, primary circuit current will never mix with secondary. Here there is no current in this branch. Current in this branch is going to be how much? 0. Right. So what you can do is you can apply Kirchhoff law here. Apply Kirchhoff law. If you apply Kirchhoff law there, sum of EMF equals sum of potential differences. EMF of the cell here is P. Current is going across that. Potential difference across AC, I name this AC, here AC, here B. So potential difference here, I RAC. So P is equal to I RAC is rho simple L over A. There you go. Right. So when another resistor is connected with P, when another resistor is connected with P, right, be careful now. What do you mean by another resistor is connected with P? Now, if you connect another resistor with P, maybe in series, maybe in parallel. I think what they meant here was connected with P means connected here. What will happen? What will happen? Look at the board carefully. Look at the board carefully. This is what will take place. This is what will take place. Here you go. Look at the board now. Battery is here. Potentiometer primary circuit. Here there is an internal resistance. I connect another resistor. What they are asking you here is connect another resistor with P. What will happen? They are given different condition. L increases if resistor is in parallel. Okay, let's eliminate certain things. What if a resistor is connected in series? Series connection means no effect. Clear? L does not change. L increases. So this is wrong. If I connect a resistor here in series, no change. Resistor in series with P. No change in L. Why? No current passes through it. Very simple. L decreases if it is in series. Wrong. L does not change if the resistance is in series with P. Correct. So guaranteed I can say that. L does not change if resistor is in parallel. Wrong. Let's check this condition. Let's check that condition. Right. Here we go. Now if I connect the resistor here galvanometer deflection is 0, balance length is there. I take it as L dash. Here we can see it clearly. Current is passing through the circuit. Current is passing through, but no current going here, no current dividing. Current will keep on going there, primary circuit current. Secondary circuit current will keep going. That's a different story. Secondary circuit current. So there will be a current I1 going through here. I can apply Kirchhoff's law there. Right. Look at the board now. Things what you learned. You already know this. Now what is the voltage balanced here? What is the voltage? Look at the board. This is your cell. The actual voltage coming out of the cell is what? Terminal potential difference. Terminal potential difference is, look at the board now. Terminal potential difference is, if the voltage is P minus I1R. Not P minus IR. Voltage reduces. If voltage reduces, balance length here will also reduce. If I apply Kirchhoff, look at the board. If I apply Kirchhoff, sum of EMF equals sum of potential differences. Here the voltage is terminal potential. P minus I1 simple R. That is equal to I times RA C dash. Here C dash, here A, here B. P minus I1 simple R. Rho L dash over A. Current will not change, rho will not change, area will not change. Here terminal PD has reduced. Terminal PD has reduced means length will also reduce. So if I connect the resistor parallelly, terminal potential difference will cause the voltage to reduce. Terminal potential difference causes voltage reduce means balance length will also what? Reduce. Why? At the balance point, current through the galvanometer is going to be how much? 0. Current through the galvanometer is going to be 0. Right. So here, now you have terminal potential difference. Terminal potential difference is less. Lesser terminal potential difference means lesser balance length. Clear? Right. Write a small sentence there. Don't write all of this. If we connect a resistor in parallel, we can say that the terminal potential difference will be balanced along the potentiometer wire. The terminal potential difference will be balanced along the potentiometer wire. Therefore, since the terminal potential reduces, the balance length will also reduce. Balance length will also reduce. So don't forget that terminal potential reduces. This part is a constant, so balance length will reduce. Okay, right. So L increases if it's connected parallel. Wrong. Correct answer is answer number 5. Right there. If we connect a resistor in series with P, if we connect a resistor in series with P, there is no current passing through. There is no current passing through. No current passing through. Therefore, the balance length will not change. Therefore, the balance length will not change. Right. Moving on. Question number 6. In the circuit shown, internal resistance of the cells is negligible. The voltage across XY. Right. So these are open terminals. Here you have open terminal. Open terminal means no current here. So current should go through this. Current should go through that. So if I apply Kirchhoff law, minus to plus, minus to plus. Sum of EMF equals sum of potential differences. Minus to plus positive, minus to plus positive. Loop direction, current direction 100I plus 50I. 15 equal 150I. I is equal to 0.1 amperes. Right. Great. Now they want the term potential difference across X and Y. So how will you find it? Very simple. You have learned this. I have taught you this. Take a smaller loop. Well, I'll take this smaller loop. This smaller loop. Arrow is going from X to Y. So if you want, name this A, B, C, D, E, F, A. This is A, B, C, D, E, F, A loop. Now I am applying the smaller loop here. A, B, C, F, A loop. Sum of EMF equals sum of potential differences. Look at the board, look at the board. Here, remember when I taught you all, now the theory ones I taught you all how to find the potential difference across a capacitor. Same way. Here minus to plus positive. Loop direction, current direction same. 100I. Here minus to plus positive. Now this loop arrow is going from X to Y. So voltage X to Y. X voltage is higher. Simplify this carefully. Simplify this carefully. 15 equal 100 times I is 0.1. 15 equals 10 plus Vxy. Vxy magnitude is equal to 5 volts. 5 volts. Correct answer is answer number 3. Correct answer is answer number 3. Vxy 5 volts. Okay. Vxy 5 volts. So bigger loop apply. Then you apply for the smaller loop. Remember the loop arrow is going from X to Y. So Vxy. The loop arrow is going from X to Y. X to Y it's going. Can you remember terminal potential difference the way I taught you? That exact way. Right. Next one. If the internal resistance of a cell in a circuit is negligible, current I in the circuit can be increased to 3I by connecting another resistor of value. Another resistor of value. Now, if you are going to increase the current, the effective resistance should not reduce. Logic. If you are going to increase the current by 3 times, the effective resistance should reduce by 3 times. Okay. That means you can't connect in series, you must connect in parallel. So how do you connect it so that the effective resistance reduces? By 3 times. Have a look. Effective resistance reduces by 3 times. If I put 2R, 2R, 2R over 3, that won't work. No? What about R over 2? R over 2 times R squared over 2, 3R over 2, yes. Correct answer will be R over 2 parallel with R. Correct answer number 5. The reason is very simple. If I connect R over 2 here, look at the board now. Here the effective resistance or equivalent resistance can be found. How do I find the equivalent resistance? I taught you a shortcut. From there, these two resistors, quickly you can say, what is it? It's R over 3. So resistance has reduced by 3 times, current will increase by 3 times. So here 3I, here I. Same battery. If I multiply these two, it should be IR. If I multiply these two, it should be IR. Okay, no? So here, don't forget, the new current here, I dash, is going to be 3I. Correct answer is answer number 5. Right there. To increase the current by 3 times, the resistance must reduce. The effective resistance must reduce by 3 times. The effective resistance must reduce by 3 times. So we can easily find the relationship. Right. Next one. The electrical energy costs 5 per kilowatt hour. To operate an electrical appliance of resistance 60 ohm. So let's find the energy. Energy is what? V squared over R is power times time. Power into time is energy. 240 volts squared, resistance is 60, time is 6 minutes into seconds, 360. 60 times 1, 60 times 6. 240 into 240 into 6. How much? You get your answer in joules. I want my answer in kilowatt hour. 240 into 240 into 6 divided by, what is kilowatt hour? 3000. 1 kilowatt is 1000. So much. Simplify very carefully. 2 zeros cancel off. 2 zeros cancel off. 12 times 2, 12 times 3. 3 times 1, 3 times 8. Simplify. 16 times 6, 96. 96. 10 to the power minus 3. 96, 10 to the power minus 3. 96, 10 to the power minus 3. So much of joules convert to kilowatt hour. So kilowatt hour is 0.096 kilowatt hour. So 1 kilowatt hour is 5 rupees. 0.096 kilowatt hour is going to be 5 multiplied by 0.096. 45, 48. 3 decimal places. 0.48 rupees. That is 48 Earth seconds. 0.48 rupees. 0.48 rupees. Simple. So here joules I divide by 3600 10 to the power 3 to convert to kilowatt hour. So here unit is kilowatt hour. 1 kilowatt hour 5 rupees means for so much how much? 0.48. 0.48. Okay, no? Right. Look at this carefully. The force required to increase the length of elastic string by a unit length is given by K. So force per length is given by K. Right. Consider the following statements made about K. Please look at the board carefully. Young's modulus is, I'll move this up a bit. Okay, now look. Young's modulus is stress over strain. Stress over strain. Stress is equal to force divided by area. Strain is extension divided by initial length. Simplify this. Force over area. Young's modulus x over L. Force is equal to A times Young's modulus over L times x. Look at the board carefully. If you look at the board carefully here, but all of you want to know F is equal to Kx. Compare K is equal to A Young's modulus over L. Look at the board now. The value of K can be increased by increasing the Young's modulus, correct? K proportional to Young's modulus. Young's modulus increases, K increases, A statement is correct. Next one. Value of K can be increased by increasing the area. K proportional to area. Area increases, K increases. B correct. Value of K can be increased by decreasing the length. Yes. K is inversely proportional to length. Reduce the length, increase the K. C is correct. All A, B, C are true. All A, B, C are true. Okay? All A, B, C are true. Very easily you can get the answer. Don't forget now. Very simple work. Very simple work. Right. Okay. A loop made of a string length L is kept on a soap film. So loop has a length L. Loop has a length L. Kept on a soap film. Kept on a soap film. Right. Soap film. Here you go the soap film. Here you go the soap film. When the section of the film inside is broken, the tension in the string becomes T. Tension in the string becomes T. If the length of the string is 2L, then the tension would be how much? Be careful. If you break the film, what will take place? Look at the board. Here length L, circumference length L. Film is here. If you break the film, it will expand, right? From the surrounding there is soap. From the surrounding there is soap. Surrounding there is soap. Huh? Surrounding there is soap. Surrounding soap molecules will pull the string. If surrounding soap molecules pull the string, what will happen? Let me go back to basic work. Right. Look at this. So these are interesting but important work. Huh? What about this color? Is it good? No. Right. This color is good. Right. Observe this carefully. Now you have the center soap film broken. Center soap film broken. Soap from surrounding is pulling this. Remember when you talk about soap, how many surfaces you have? 2 surfaces. Now because it's pulled, what you can do is, if you take a cross-sectional area, this part, from this corner there is going to be a tension. This corner there is going to be a tension. This corner there is going to be a tension. Look at the board. I'll visibly draw it different color. This corner there is going to be a tension. This corner there is going to be a tension. There you go. Who is balancing this? The pull by surface tension in one direction. Pull by surface tension in one direction. Look at the board. What we can say is, please understand this, it's a very simple concept. This is equivalent to a rod equal to the diameter. A rod equal to the diameter. Both ends there is tension. Both ends there is tension. And along this rod surface tension force is acting. Along this rod there is a pull due to surface tension. Along the rod there is a pull due to surface tension. So remember here, surface tension is pulling it in all directions. Surface tension is pulling it in all directions. Surface tension is pulling it in all directions. They are directed towards the center, but they are being pulled in all directions. They are being pulled in all directions. So there you go. Right. So these pulled in all directions. If I take a cross section, tension from these two ends is balanced by the surface tension force. The surface tension force is the surface tension force along the diameter. Surface tension force along the diameter. Right. Let's look at this carefully now. So circumference is 2 pi r, that is L. Pi times 2r is diameter, that's L. Diameter is equal to L over pi. Right. What is the surface tension force? Force divided by length is surface tension. Surface tension gamma multiplied by the length is diameter. Soap will have how many surfaces? 2 surfaces. Soap will have 2 surfaces. Look at the word now. What can you say here? Upward forces balances downward forces. From here we can say sum of forces in the upward direction balances sum of forces in the downward direction. For this one. Upward direction gamma d times 2. Downward direction 2t. 2 cancel off. Tension is equal to gamma d. Tension is equal to gamma d. What is diameter? L over pi. L over pi. So what is your surface tension? Gamma L over pi. Gamma L over pi. This is just the idea. This is just the theory. So very simple idea. Very simple idea. Okay. More than theory, this is how we solve it. This is how we solve it. Right. So here surface tension will pull it in all directions. Surface tension will pull in all directions. So to find the tension, there is no other way. To find the tension, you must take a cross-sectional area. If you take a cross-sectional area, from this corner also there is a tension, from this corner also there is a tension. And that is balanced by the surface tension force. Remember, the surface tension force here is equivalent to the surface tension along the diameter. Equivalent to the surface tension along the diameter. So tension forces balanced by the surface tension force. Gamma into d is surface tension into length. Soap has 2 surfaces multiplied by 2. So surface tension is gamma L over pi. Look at the board. You have your answer here. Tension balances or tension proportional to length. Tension proportional to length. So if length doubles, tension also will not double. Length doubles, tension also will double. So if you go here, length doubles, tension also will double. Correct answer, answer number 2. Correct answer, answer number 2. Clear? Right. So I want you all to write this carefully. So here a very simple but powerful example. Very simple but powerful example. Right there. When we put the string into a soap film, when we put the string into a soap film and break the center film and break the center film. Break the center film. The surface tension will pull on the string in all directions. The surface tension will pull on the string in all directions. Creating a tension along the string. Creating a tension along the string. Creating a tension along the string. Tensions on both ends will be balanced by the surface tension force acting on one half. Tension on both ends will balance the surface tension force acting on one half. Will balance the surface tension force acting on one half. On one half. And one semicircle is mathematically similar to the force, the surface tension force on the semicircle. The surface tension force on the semicircle is similar to the surface tension across the diameter. The surface tension across the diameter. So F is equal to gamma d times 2. The surface tension along the diameter. Surface tension along the diameter. Since soap has two surfaces, we multiply by 2. Since soap has two surfaces, we multiply by 2. I hope you remember the definition of surface tension. Surface tension is force per length, width and dimensions per inch. So multiply this by the length, length is the diameter. Will give you force. Two surfaces there means you multiply this by 2. Upward forces balances downward forces, tension can be found. Gamma is constant, pi is constant, tension proportional to L. So if the length is 2L, tension is double. Right? Write down carefully. Important workings. Okay, right now. Right. Question number 11. Question number 11. Read. Figure shows an attempt made by a man to hold a bull tied to a rope. Okay. The force at X acting on the bull's leg is Fl. So bull, there will be two forces. Is pushing the flow backwards. Flow is pushing the bull forward. And here normal reaction. That will give us a resultant force acting in that direction. Resultant force acting in that direction. Okay. So here there is a normal reaction. Bull is pushing the flow backwards, flow is pushing the bull forwards. So because of these two, there will be a resultant force there. So I can erase these two forces. I'll erase these two forces. So which will give us a single force here. Single force here, force on the leg. And that on the ground, every action has equal opposite reaction. Force on the ground equal opposite Fg, right? Right. Okay. The force at Y acting on the rope is Fr and on the hand is Fh. So man is pulling the rope behind, rope is pulling the man forward. So on the rope, Fr, on the hand, Fh, on the hand, Fh, okay, on the hand, Fh, right? Okay, no? So where is this given? FL, FG, FR, FH. Correct answer, answer number 2. Correct answer, answer number 2. Okay. Correct answer, answer number 2. Right. Moving forward. A beam of light that appears to be converging at a point 10 centimeters behind the lens is actually converged to a point axis 8 centimeter behind it. What is the lens? So actual converging means convex lens. Huh? So what's happening is this light, convergent light, seems like to converge 10 centimeters behind the lens. 10 centimeters behind the lens. But it actually converges to 8 centimeters there. 8 centimeters there. So incident rays seem like to me, this is your object. What object? Virtual object. Virtual object. This is your image. What image? Real image. Virtual objects will give real images. Virtual objects will give real images. Now apply lens equation. 1 over V minus 1 over U equal 1 over F. Object distance is in the direction light travels. Image is also formed in the direction light travels. Focal length we don't know, without putting the sign convention fine. Here minus 1 over 8 plus 1 over 10, that is equal to F. Carefully look. That is equal to F. So right now, in the direction light travels, all measurements are minus. In the direction light travels, all measurements are minus. So therefore, if you simplify this, 40 minus 5 plus 4, 1 over F. Minus 1 over 40, 1 over F. From this we can say F is equal to minus 40 centimeters. Minus 40 means convex lens. Convex lens of focal length 40. Answer number 1. Right there. The incident rays seem like to meet at 10 centimeters. The incident rays seem like to meet at 10 centimeters. Incident rays seem like to meet at 10 centimeters. This means it is a virtual object. 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 And it will actually converge, will form a real image. It will actually converge to form a real image. To form a real image. Right. One end of a string of mass per length is simple length. There you go. Is connected to a prong of tuning fork. Other end is connected to mass end passing over. The string forms standing wave pattern. How many loops? 1, 2, 3, 4 loops. That means n equal 4. That is technically fourth harmonic. fourth harmonic. Very simple. So what can you say about the frequency? F is equal to n over 2L square root T over simple m. N is 4 over 2L. Tension is equal to capital Mg over simple m. 2 over L, capital Mg over simple m. 2 over L means answer number 1. Answer number 1. So 33, answer number 1. Okay. 33, answer number 1. Right. Question number 14. Two strings A and B. Two strings A and B are connected end to end. Right. And the free end of the lighter string B is attached to a rigid ball. So rigid ball means expect a rough reflection. Rough reflection to take place. Rigid ball. Rigid vertical ball. Mass per length of A is 0.04 and that of B is 0.01. So velocity of A is equal to square root T over m. Tension is same, mass per length 0.04. So 2 decimal 100 divided by 4, 24, 25. 25 square root is 5 square root T. Right. Velocity at A is 5 square root T. Right. What about the velocity at B? Velocity at B, same tension, T divided by mass per length is 0.01 square root. 100 square root is 10 root T. So velocity here is faster. Velocity here is faster. So here velocity is slower. Slower means denser region. This is going to be faster, therefore rarer region. Denser, rarer goes away, right? The composite rod is first pulled by hand to create 1 Newton tension. So technically 1 Newton tension acting means this is 5 meter per second. This is going to be 10 meter per second. Very simple. Tension is equal to 1 Newton. Right. After the pulse has reached point P, what will happen? After the pulse has reached point P, what will happen? Look at this. Here denser connected to rarer. Clear? Speed is going to be much more slower. Speed is going to be much more faster. Denser, rarer. Here mass per length is also large. Mass per length is also large. So this end here, what can you say about that end? That end there. Look at the board carefully. So here you can see this wave will come, this wave will come, a non-inverted pulse would travel along B to the right with speed 10. So here speed is 10, this looks correct, looks okay. An inverted pulse would travel along B to the right with the speed 10. Inverted pulse will travel along B to the right with speed 10. So there would be an inversion, same direction, refraction, B is wrong. A non-inverted pulse would have travelled to the left along A. Along A. A non-inverted pulse would have travelled to the left along A. Here rigid, so there will be an inverted pulse. These are wrong. An inverted pulse would have travelled to the left along A with speed 5. To the left of A. To the left of A with speed 5. Inverted pulse would travel to the left along A with speed 5. Clear? So here yes, it will not be inverted. No pulse will travel. That's wrong. So here look at the fourth one. Look at the fourth answer. What can you say? What can you say? Here, smooth connection here. Smooth connection here. No inversion taking place. So these are also wrong. So only correct statement in the figure is going to be 1. A non-inverted pulse would travel along B to the right with the speed 10. Non-inverted pulse. Okay. Write a small sentence. Let's say here refraction will take place. Here refraction will take place at point P. And since the diameters are same, smooth reflection will take place. And since the diameters are same, smooth reflection will take place. Smooth reflection will take place. So the reflected wave will be in the same phase. So the reflected wave will be in the same phase. And the refracted wave will also be in the same phase. And the refracted wave will also be in the same phase. Refracted wave will also be in the same phase. Okay. Right. A gas is confined to a closed container. Consider the following statements made regarding the speed of sound of gas. Speed of sound of gas depends on gamma RT over molar mass square root. Also you can say gamma P over rho square root. Right. Speed of sound does not change when the volume of the container is changed at a constant temperature. So when the volume is changed, density will change. When density changes, pressure might be affected. Be careful. Pressure might be affected. But if you look at this, speed of sound does not change when the volume of the container is changed. Right? So when the volume changes, pressure will change. When the pressure changes, proportionally density will change. When density changes, velocity of sound in air will not change. Statement A is correct. Right there. When the volume changes, pressure will change. When the volume changes, pressure will change. When the pressure changes, density will also change. When the pressure changes, density will also change. When the pressure changes, density will also change. Therefore, there is no change in the velocity of sound in air. Therefore, there is no change in the velocity of sound in air. Therefore, there is no change in the velocity of sound in air. Right. B. Speed of sound changes with temperature. Yes. B proportional to square root of absolute temperature. Correct. B is correct. B proportional to square root of absolute temperature. Therefore, that is correct. Speed of sound changes when more gas is added to the container at constant temperature. More gas is added means density will change. V proportional to 1 over rho. Rho increases or rho changes, V will change. Correct. A, B, C all are true. A, B, C all are true. Right there. When more gas is added, so wait till speed of sound changes when more gas. Here also gas, not a different gas. Now if a different gas is added, that's it. Look at this, huh? So be careful. That's why I double checked it. More gas means here the same gas. If you are adding the same gas, what happens? If you are adding the same gas, more gas is added, density will change. Also, you know, pressure proportional to density. Density changing means pressure will change. Speed of sound will not change. So correct answer only A and B. Correct answer only A and B. Now what if this was a different gas? If I had put a different gas, more of the same gas, wrong. Different gas means effective molar mass will change. Effective molar mass will change means what? Then velocity will change. But if I am adding the same gas, no change. Right there. If more gas is added from the same type, if more gas is added from the same type, right. If more gas of the same type is added, density changes, pressure will also change, velocity of sound in air will not change. But if a different gas is added, so that's a very important point. Huh? Different gas is added. So different gas is added. So what will happen? Effective molar mass will change. 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 Therefore, V will change. So here the same mass is added. Same gas is added. So that's why only A and B correct. Right. A driver sitting in a parked car sees another car moving towards him. So there is another car moving towards him. This fellow is parked at rest. And he will be the source. He will toot the horn. Sound will travel with a velocity v. Observer is here. Observer is also coming with a velocity u. So apparent frequency here f dash. Actual frequency is 340 Hz. So you all know the rule. Velocity of sound with respect to observer, v plus u. Velocity of sound with respect to source, v into actual f. Here velocity of sound in air, is given. Velocity of sound in air is given 340. Speed of the car we don't know. 340, frequency also 340. Apparent frequency 348. 340 cancel off. U is equal to 8 meter per second. U equal 8 meter per second, answer number 5. U equal 8 meter per second, answer number 5. Right? Okay. Question number 70. Question number 70. Statement question. Good one. I'm sure you have negotiated this earlier. Temperatures at two ends of a composite rod made of two similar pieces of different metal. So here are maintained at 100 and 0. The composite rod is well lagged. Thermal conductivity of P is twice that of Q. So 2K here, K here. K here, 2K there, right. Statement regarding at steady state. Temperature variation along the composite rod from hot end to cold end is the same in both situations. I am afraid wrong. Temperature variations are not the same. I am drawing show you. Temperature at the junction between two metals is higher in situation A than in situation B. Higher in situation A than in situation B. rate of flow of heat along the composite rod is the same, right? So whether you put the front rod, back rod, front and back, effective K is same. So this is correct. C is correct. C is correct. A is wrong. So whatever with A is wrong, this is wrong, this is wrong, this is wrong. Let's check and see B and C. Right. Now if I draw this fellow, right, no space is given, so I'll use the board. I'll use the board. Right. Look at the board carefully. This is one. This is the other one. Here 2K, here K, here K, here 2K, here 100 degrees Celsius, 0 degrees Celsius, 100 degrees Celsius, 0 degrees Celsius. Effective heat capacity is the same. So the Q dot across this is the same. Q dot across this is the same. Q dot is equal to Ka delta theta over delta L. Look at the board carefully. Here Q dot is constant, area is constant. K increases, this will reduce. K reduces, temperature gradient increases. Right. Now let me draw it here. Let me draw it here. Let me draw it here. There you go. Now look at the board. Larger K means smaller temperature gradient. Smaller K means larger temperature gradient. 0, 100. This is in figure A. I'll draw both together easier. What about figure B? K is small, gradient is large. Next is K is large, gradient is small. This is figure B. What can you say? Intermediate temperatures are different. But the effective K equivalent is same. K equivalent is same. Right? Because every dimension is identical. So right now if you fold this, temperature at the junction between two metals of the composite rod is higher in situation A. Situation A is higher. Wrong. Situation A is not higher. Situation A is lower. 2kk. 2kk. If you want, go back and see. 2kk. 2kk is lower. K2k only is higher. Oh, sorry. Again the question. Figure A is higher. Figure A is higher. Ah, yes, correct. If they are asking higher temperature, yes. This is correct. Higher temperature, rate of flow, heat same. B and C correct. B and C correct. So temperature at the junction between two metals is higher in situation A. Right. You can write the one in the whiteboard, in the board. So here Q dot is same, A is same, K large, gradient is less. K small, gradient is large. Here K small, gradient is large. K large, gradient is less. So the correct answer there is B and C both correct. B and C both correct. Right. Okay. Moving on. Figure shows an isolated system of three masses. The mass M is at under the influence of masses M1 and M2, which are held in positions. When mass M is double, M1 is double, M will remain at rest if R2 is changed to. Right. Let's look at the forces here. Here there is an attractive force Here there is an attractive force. So if I write here, F1 is equal to F2. F1 is equal to F2. Write the equation value. Capital G M1 capital M divided by R1 square. R1 is equal to 3A square. What is M2? F2 here. Capital G M into M2 divided by distance between these two masses 2A square. 2A square. Simplify this carefully. Simplify this carefully. M1 divided by M2 is equal to 9 divided by 4. Right. Keep it like that. Now what are they saying? When this mass is doubled, what will be the value of R2? I'll close this. So here F1 dash equals F2 dash. F1 dash equals F2 dash. I am drawing in the same diagram. Otherwise, in vain. Masses are capital G, capital M. To M1 distance is equal to 3A square. Here capital G, capital M. Mass there is M2 divided by distance R2 square. R2 square. GM cancel off. Simplify this. M1 over M2, that is 9 divided by 2 R2 square. 9 divided by 2 R2 square. What is M1 over M2? M1 over M2 is 9 divided by 4. 9 divided by 2 R2 square. 9 cancel off. 2 times 1, 2 times 2. First multiply. R2 square equal to R2 is equal to root 2. R2 is equal to root 2. The A will come. No? Here the A also will come. 9A square. 9A square root 2A. So R2 is equal to root 2A. R2 equals root 2A means correct answer is answer number 2. Correct answer is answer number 2. Simple work. Right. Moving on. The equivalent capacitance between A and B. Okay, nice. So if you look at this, these are connected to B. B. Okay, no? These are connected together non-resistant wire. We'll call it X. We'll call it X. We'll call it X. X. Here X. Here X. Here Y. Here Y. Here Y. Here Y. These are X. Right. So Y here, Y here, Y there. X here, X there, X there. Here was X. Here A is there. Here Z. Z is here, Z is here, Z is here. Right. Can you rearrange this? Yes, we can. A we have one capacitor connected. Here we have C connected. Here Z, sorry. Z is connected. Z is connected to three more capacitors. Z is connected to 3 more capacitors. Okay. Z is connected to 3 more capacitors. So here one Z is there, 2 more. So 2 more we can say one plate here, one plate here. Z plates. These Z plates, one is connected to X. One is connected to X. One is connected to Y. One is connected to Y. X connected to how many plates? One here, one there, one. 3 plates. 3 more plates. 1, 2, 3. These all X plates. Here 1, 2, 3. Y is connected to how many plates? 3 plates. One is connected here. The other two are connected separately. Y plates. Let me draw this in a different way for you. This looks a bit complicated for all. Simpler notation. Simpler notation. Look at the board. From this itself. Can I connect this to here and here? Can connect. Non-resistor. Non-resistor. I can connect. So let me draw. Connected here, 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 here. Right. Connected like this. Here there is a capacitor that is connected like this. That is connected like this. Here one more capacitor A, here B. Look at this carefully. These two terminals. Here C, here C, here C, here C. Can you see there is a Wheatstone bridge here? Can you see there is a Wheatstone bridge there? Always remember to look into a Wheatstone bridge. C divided by C, C divided by C, same. This can be cancelled out. If that is completely cancelled, what will you get? Here you have capacitor. Here you have capacitor. Here you have capacitor. Capacitors in parallel are like resistors in series. 4C. Capacitors in parallel are like resistors in series. 2C. Here C. Here A. Here B. Capacitors in series are like resistors in parallel. So 1 over C equivalent is 1 over C, 1 over 2C, 1 over 4C. 4C common, 4 plus 2 plus 1, that's going to be how much? 7 over 4C. Turn upside down, C equivalent, 4C divided by 7. 4C divided by 7, answer number 5. 4C divided by 7, answer number 5. Right there. We can clearly see a Wheatstone bridge created. Now why can I connect this here? The non-resistant, same potential. Why can I connect this there? Same potential. So this branch here, if you take this branch here, or even better, this branch here, Wheatstone bridge. Wheatstone bridge. Once it is a Wheatstone bridge, you can remove the center capacitor. You can remove the center capacitor. Okay. Right. Okay. Question number 20. In the circuit shown, the internal resistance of all the cells are negligible. Current in the circuit is I. Current in the circuit is I. Which of the following equations is true? So let's apply Kirchhoff law. Let's apply Kirchhoff. Let's say going this way. So apply Kirchhoff law. Minus to plus, minus to plus, plus to minus. Sum of EMF equals sum of potential differences minus E1 plus E3 plus E2. Loop direction, current direction same. So I times R1 plus R2 plus R3. Right. So this is not the first one. Can't be the second one. So either 1 or 2 should be negative. E2, E3 positive minus E1. Correct answer is answer number 4. Correct answer is answer number 4. Very simple. Apply Kirchhoff law, you can get your answer. Apply Kirchhoff law, you can get the answer. Right. Okay. Structured essay question. Structured essay question. Structured essay question. Figure shows some of the apparatus provided to you to experimentally determine the electric power dissipated as heat from a 230 volt 25 watt bulb. Right, 25 watt bulb. You are asked to use water to collect the heat given out. Complete the above diagram by indicating the other required apparatus to show the experiment setup you would use for this experiment. Right. Well, this is connected to the socket here. Water is filled almost up to the brim here like this. You make sure it doesn't touch the exposed surface. You will need a stirrer, you will need a thermometer, and you will need a cover. Correct. Complete the above diagram by including other apparatus. So here stirrer is there. Thermometer is there. These wires are connected as well. Right. Okay, done. Next one. Mark on the diagram the level up to which you fill water. So I fill water up to this level. I don't go beyond it. Up to the level here. If you go beyond it, short circuiting might take place. Clear? Because the wire will start getting touched. It will start touching the water right there. We must make sure that it doesn't touch the exposed wire connected to the supply. Right. Mark on the diagram the level up to which you fill water. Done. Right. This part is done. Right. Give 2 reasons as to why it is suitable to use a small beaker. Right. Smaller the beaker, smaller the mass, greater rising temperature. In a shorter time. Greater rise in temperature in a shorter time. That is one main reason. Next one. Surface area is less. Heat loss to the surroundings. Is minimized. Minimum. Heat loss to the surroundings is minimum. So you're making sure the surface area exposed is less. Heat loss is Ka theta minus theta r, Newton's law of cooling. So by reducing the surface area, you're reducing the heat loss to the environment. Okay, right. Give a list of apparatus needed to take measurements in this. So what's the list you need? You need a thermometer, thermometer, you need a scale, preferably triple beam balance, and what else? You need to measure time, no stopwatch. Stopwatch is needed. Stopwatch is needed. Because once you measure time, you can find the energy. Right. When this experiment was performed with 230 volt 25 watt filament bulb, the temperature of water was increased from 28 to 37 in 10 minutes. Mass of water used was 240 gram. Estimate the electrical power transfer. So power multiplied by time is equal to MW SW delta theta. Power into time 10 minutes, 600 seconds. Mass of water is equal to 0.24 kilogram, 4200. Specific temperature change 37 minus 28. 37 minus 28. Simplify this. You will obtain the relationship 15.12 watt. 15.12 watt. 15.12 watt. Okay. The value obtained in D may not be exactly equal to the power dissipated as heat from the bulb. Give two possible modes of heat loss. Now, how can heat can be absorbed? Heat can be lost due to conduction, convection, radiation. Heat loss may occur. Also, some of the water might vaporize. Why some of the water might vaporize or evaporate? Evaporation, heat loss also might take place. So, bulb holder, insulated layer, beaker. So, there can be heat loss due to convection. Convection in water, convection from the vessel. Also, there can be what you call heat loss due to radiation. Okay. Heat loss due to radiation. Also, there can be heat loss due to evaporation. Right there. So, we can write there. We can write here. Heat loss due to convection. Heat loss due to convection. Next one, heat loss due to evaporation. Heat loss due to evaporation. Heat loss due to evaporation. So heat loss due to convection, heat loss due to evaporation. So heat absorbed by the vessel. Heat absorbed by the vessel. So also heat loss due to radiation. Heat loss due to radiation. Why? When the temperature increases, radiation heat loss will increase. Right. Certain manufacturers indicate maximum power in electric lampshades. Briefly explain the reason why. So electric lampshades, if you all remember this, here the bulb is there. Bulb will give out heat. This heat is going to be absorbed by the lampshade. If there is no minimum power rating, the lampshade can catch on fire. Where? The lampshade can catch on fire. Right there. The heat given by the bulb, will be absorbed by the lampshade. And if the heat is greater than the minimum, the lampshade can burn. the lampshade can burn. Guaranteed in your home, you might have a lampshade which is burnt somewhere. Guaranteed you have a lampshade which is burnt. Okay. Right. Going upwards. Essay question. So you can see the structured essay question. They are asking practical things. Now you have not done this experiment in school. We don't take light bulbs and put inside water and do the experiment. No. Using the experience you have got by doing calorimetry experiment. Here they are asking you how the general experimentation will take place. Remember, these kind of creative structured essays also can be put. Don't think 100% they are going to give from your what you call lab experiments. Lab experiments plus practical knowledge. There are some creative structured essays that can be created. Okay, right. Read the following paragraph. Now, when you have a paragraph question, number 1, best is you start from the question. Don't waste time reading. Right. What physical property of the sound wave determines the loudness of sound? Now, loudness depends on amplitude, but let's see what they have told. So, a source of sound including musical notes is vibrating object. Sound is characterized by its loudness, its pitch, and the third quality called quality of sound, which enables us to distinguish between a type of musical instrument from the other. I gave the experiment, remember, famous violin and trumpet and piano. Quality of sound enables us to distinguish a type of instrument. For example, note is played separately in a violin and a flute. The same loudness and the pitch. There is a clear difference in the two sounds. This is the difference in quality of sound. Just as loudness and pitch can be related to measurable quantities of the sound wave, so too can be quality. Generally, when a note is played in a musical instrument, overtones are present in addition to the fundamental frequency of sound. Quality of sound depends on the number of overtones and their relative amplitudes. Overtones and their relative amplitude. Now, they have not told you, which means you should know. So sometimes the answer might not be there in the paragraph because you should anyway know that. It's part of basic theory. So loudness depends on amplitude. Amplitude of sound. Larger the amplitude, greater the loudness. What is the physical property of sound wave? Associated pitch. Frequency of the sound wave. There you go. Frequency of the sound wave. Okay. Frequency of the sound wave. Right. Fundamental frequency F0 of the Fourier spectrum of a violin is shown in figure number 2 is 400 Hz. What is the frequency of the third overtone produced by the violin? Right. Go back to. Now read this. Figure 1 shows a sound pattern of a violin. It indicates the variation of total amplitude of sound produced. Figure 2 shows the Fourier spectrum of the sound and the given frequencies of its fundamental overtones and their relative amplitudes. The Fourier spectrum is generated from sound pattern using mathematical technique called Fourier analysis. Remember, once you go to university, you will learn Fourier analysis. Your integration should be perfect. Fourier analysis and Laplace analysis. Don't forget this. Someday if you go to university, if you are learning science or mathematics or physics in detail, guaranteed Fourier analysis will come, Laplace analysis will come. Fourier, what they have done is, this amplitude, look at this amplitude, different amplitudes, different times. What they have done is, the Fourier spectrum of this pattern given the frequencies of its fundamental and its overtones and their relative amplitudes. The Fourier spectrum is generated from sound pattern using mathematical technique called Fourier analysis. You can convert this wave into signal pattern like this, ones and zeros. Sounds which are normally called noise have a nearly continuous Fourier spectra rather than discrete spectra. So noise, background noise, have continuous spectra rather than discrete spectra. Discrete spectra, right? Read carefully. So this is a nice question. Today we have electronic organs that can reconstruct music produced by any musical instrument available to us. So you can play the note and then you can synchronize it, synthesize it, and then you can play on top of it. No, that's because of this technology, Fourier. For such reconstructions, first the Fourier spectra of the musical notes, read carefully. Fourier spectra, so reconstruction. For such reconstruction, first the Fourier spectra of the musical notes must be obtained. After that, it is possible to electronically generate electronic wave patterns for each note by mixing electrical signals having frequencies and their corresponding relative amplitudes present in the Fourier spectrum. These electrical wave patterns that can be converted to sound waves, all these can be done in near perfection using digital techniques. Check and see how many people who can't sing are singing. If you make them to sing live, they can't sing. But if you make them, or if you give them what you call digitally to sing, yes, they will sing. There are some fellows who are horrible singers, but they can sing in a music video or whatever. That's because it's digitally mastered. All their problematic off-pitch areas are digitally corrected. Okay, right. So this is a nice section, nice question. In standard musical instruments, the source is set into vibration by striking, blowing, plucking, bowing. Bowing means like this. Plucking means like a sitar or guitar. Blowing means trumpet, saxophone, all blowing instruments. Striking means drum, dun, dun, dun. Okay, right. Here, the flute and the trumpet make use of vibrating columns of air to produce musical notes. Yes. Closed tube is used. Flute can be considered as a tube with both ends open. Flute considered as both ends open. When the flute is played, air inside is resonating. Right. Violin, guitar and piano all have vibrating strings connected. Yes, these are butt piano, not the electronic piano. These is the grand piano. In guitar, different musical notes are obtained by vibrating the vibrating length of a string using fingers. The guitar has several such strings to produce required notes. In piano, there is a separate string for each note. In general, the mechanical vibrations in thin strings do not produce loud enough sound to be heard. Thinner the string, smaller the diameter. In string instruments, therefore, a sounding box means what? Sonometer, like your box guitar, is used to amplify sound. There you go. When strings are set to vibrate, sounding box resonates with the same sound, producing much stronger sound. However, in electric guitars don't have boxes. Mechanical vibrations are converted to electrical signals, subsequently amplified electronically. Right? So, nice set of knowledge here. Right. So, right, the fundamental frequency F0 of the Fourier spectral violin is shown in the figure. 2 is 400 Hz. That is the Fourier spectra. Right. So here, this is Fourier spectra 400 Hz. 400 Hz. Right. The Fourier spectra here. Fundamental frequency for a guitar. Here. Fundamental frequency for a guitar. For a violin or guitar, right? What is the frequency of the third overtone produced by the violin? Right. What do you mean by third overtone? Third overtone is fourth harmonic. Fourth harmonic is here. Fourth harmonic is here. So third overtone is fourth harmonic. Fourth harmonic is 4 times the fundamental frequency. 400 times 4 is 1600 Hz. 400 times 4 is 1600 Hz. Let me go back. Right. So here 4 times F0. 4 times 400, 1600 hertz. 1600 hertz. Right. Okay. Moving forward. What is the value of the amplitude of the fifth overtone? Fifth overtone is sixth harmonic. Fifth overtone is sixth harmonic. Yeah. Sixth harmonic. Sixth harmonic, I put inside brackets. To the fundamental frequency F0. Fundamental frequency F0. Go back. Go back. Sixth harmonic. Sixth harmonic. Sixth harmonic is 2, no? Sixth harmonic is 2. Fundamental is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2 divided by 10. 2 divided by 10, 0.2. 2 divided by 10, 0.2. So 2 divided by 10, here 2 divided by 10 is 0.2. 0.2. 2 divided by 10 is 0.2. Right. A note produced by a musical instrument has fundamental frequency 420 and the first and second overtones have each amplitude equal to 1/2 of that of the fundamental. 1/2. Assume that no other overtones are present. Draw the Fourier spectrum for the note. Draw the Fourier spectrum for the note. Interesting. Look. Fundamental frequency is 420 hertz. First and second overtone is second harmonic. Second harmonic is 840 hertz. Sorry, second overtone. First and second overtone. Third harmonic. 3 times 420 is going to be 0, 6, 12. 1260 hertz. Right. Draw the Fourier spectrum for the note. Draw the Fourier spectrum for the note. Right. Carefully look at this. Carefully look at this. Right. So 420 hertz. 420 hertz. They are telling the first and the second overtones have first overtone and the second overtone present 1/2 of the fundamental second overtone. So amplitudes are 1/2, not 1/2. 1/2. That means A over 2. So if you take the spectrum analysis like this, fundamental frequency F0, 2F0, 3F0, carefully look. Here both are same. This will be double. Half. So that will be double. Right. So actually it's not difficult. Not difficult. State the steps that should be taken to electronically generate the sound. So how do you generate the sound? Here amplitude, here frequency F. 2F and 3F0. The amplitudes are A over 2, A over 2. So they should what? Superimpose each other. Here, superimpose each other. So you can see F0. Have they given any symbol for this? No. F0, 2F0, 3F0, and relative amplitudes. 1/2 and half. Superimpose each other. superimpose each other. Superimpose each other. So all the frequencies with their amplitudes will superimpose each other. Superimpose each other. Okay. Right. Electronic guitars have no sounding box. Give the reason. So why don't they have sounding boxes? Because the sound is amplified electronically, right there. Because the sound is amplified. Because the sound is amplified. Because the sound is amplified electronically. Right. Write down an expression relating L, mass per length, fundamental frequency of a stretch string. That means you must prove it. Here fundamental frequency, length is L. So what can you say? Lambda divided by 2 is equal to L, lambda equal to L, V is equal to F naught lambda, V equals square root T over N, lambda is 2L. From this F naught is equal to 1 over 2L, square root T over simple N. There you go. 1 over 2L, square root T over simple N. Right. Okay. A 0.68 long guitar string is termed to play the fundamental note 330 when unfingered. How far from the end of this string must the finger be placed to place a note of fundamental frequency 440? Frequency inversely proportional length. Fundamental frequency 330. Length is 0.68 unfingered. You are not keeping the finger. How far from the end of this string must the finger be placed to play the note? End of this string means 440 Hertz. Now the length is L, be careful. So this length is 0.68 unfingered. Now I am keeping the finger here. From this end they are asking that distance. This only I have given. Divide the first equation by the second equation. 330 divided by 440 is equal to L divided by 0.68. 4.68 L. Here 3 times 0.1 for 28 7. 0.51 meters. So Nx is equal to how much? 0.68 minus 0.51. 0.17 meters from that particular end. 0.17 meters from that particular end. Careful. 0.17 meters from that particular end. Right. A flute is designed to produce a note of fundamental frequency 262 Hz when played at a temperature 27 with all holes closed. If the speed of sound in air is 27, calculate the approximate length. So fundamental frequency, here you go. Length is equal to L. Approximate length. Lambda divided by 2 is equal to L. Lambda is equal to 2L. V is equal to F lambda. 340 fundamental frequency 262 2L. L is equal to 340 divided by 412 5. 340 divided by 525. 0.65 meters. 0.65 meters. 0.65 meters. Okay. 0.65 meters. Right. Simple work. Very simple work. Okay. If the flute is played with all holes closed in an environment temperature is -30, what is your fundamental frequency? Frequency you can see open tube NV over 2L. F is proportional to V. V is proportional to square root T. Therefore, F is proportional to square root T. Look at the board carefully. When the frequency is 262, temperature is 27. Temperature is 262. 27 means 300 Kelvin, equation 1. They are asking what's the frequency now when the temperature is minus 30. 273 plus minus 30, 243, no? 273 minus 30, 273 minus 30, 243 square root. Correct. Divide the second equation by the first equation. F dash divided by 262, 243 divided by 300. Simplify this. F dash equals 262, 243 divided by 300. From this you can find the frequency in hertz. 262 Simplify the relationship. If you divide it, let's see. (243) divided by 300 square root multiplied by 262. So 235.8. 235.8. So length and harmonic number won't change. N is all numbers. 1, 2, 3, so on. So here frequency proportional to velocity, velocity proportional to square root of temperature, therefore F proportional to square root T. Simple working. Right. Okay, done. Right now. Okay. So far what we have done? Week number 5, day number 2. So 4 weeks done. 240, 260, 280. 280 MCQs done. 280 MCQs done. What else? Structured essay 14. Essay 14. And you can see the experience. Look at today's essay, Fourier analysis. How to solve the problem. So these kind of things they can ask. Fourier analysis means they are taking the amplitude of oscillation and giving it a figure. If the amplitude is double, the relative amplitude also is double. If it's half, so you compare it with the fundamental always. Okay. So if I go back here, so what do you mean by this Fourier analysis? Fourier analysis, we have done one relationship. Sometimes in your exam paper they might ask, what is the value of amplitude of the fifth overtone to fundamental? So fifth one to fundamental, the ratio is the relative amplitude given. So here what they are doing here in Fourier analysis here is, say a reconstruction, Fourier spectrum. What they are doing is, they are corresponding relative amplitudes. So with the fundamental, every amplitude is taken and found the relative amplitude. From those relative amplitudes, we can keep the problem solving forward. Clear? So what we have found here is actually relative amplitudes. Here we drew a relative amplitude for the violin. For the violin, we have done the relative amplitude. Sorry, for a musical instrument, relative amplitude is found. They are telling you the second and the third harmonics amplitude is half the first. So first one is double, so these are half. If I take this as 1, if I take this as 1, these are going to be half. These are going to be half. These are the relative amplitudes. Relative amplitudes. Relative amplitudes. These are your frequencies. Frequency of vibrations. Okay, no? Right. So remember, every essay question teaches you, gives you more experience. And this experience will be what helpful for you to do well in your exam. Okay. Right then. See you tomorrow. Week 5, day 3 work. Stay home safe. Keep working. Good night.